were trying to apply this stuff to underactuated robots by just adding in this extra constraint. But things became difficult when we tried to add in external forces also, which are pretty necessary for humanoid robots, I guess, because the simple problem I showed you works really well for example, satellite, where there are no external forces. Yeah, there are definitely limits on what you can do based on the fact that there's actually nothing grabbing onto the satellite and manipulating it. If you don't have thrusters, for example, yeah. Or if you're just falling in free space and there's no friction. But that's not the situation we're trying to solve here. So that was one problem. We need to still incorporate external forces with limits on them also. And the direction in which we were going. The direction in which we were going also made the size of the QP really big. So we had to add in the torques again, and we had to also add in the forces, the contact forces, and so yeah, the size of the vector that we're trying to optimize is becoming bigger and bigger. So let's try to come up with a way to make that better. And first I'll have to do a little bit of theory. So we left off last time with twists and wrenches. Now I'm going to introduce something else. It's called an inertia matrix. And I'm going to go pretty fast again. But so if you have a rigid body, let's call it I, and then there's the world, W. Then again the twist of this body in body frame is the twist of I with respect to W, expressed in frame I. So that's a vector in R6. And then this body actually has some inertia. So that's a property of the body. And if we write that inertia in body frame, then it's written as I. And that's a 6x6 matrix. Or 6x6. So that has in it both mass moment of inertia and mass and center of mass offset, if there is one. So that's sort of your equivalent of all of those things for 6D vectors.
It has special. It's not full rank, is it? I mean, it's not 9 independent elements. There's like symmetry, I think, to it, or
yeah.
some properties.
Yeah, but that doesn't really matter right now. Okay, so we need those two things because what I want to get to is this thing called momentum. H, I, and so in Dijndom's book he uses this notation to denote the momentum. Actually, H comes from Ambaris Goswami's paper, but this is what he would do for wrenches, so also for momenta, which are in the same space. So where the first one would be expressed in frame, just like for wrenches, and the second one, the body frame. But I'm actually going to prefer this notation where the body is on the bottom. And that's defined as HI equals I T I W I. So yeah, comparing this to just a single point mass, we would have mass just here as a scalar, as a 3x3 diagonal vector with all m's, times velocity would be your momentum. But now this is how you generalize it to 6D vectors. So that's momentum. And there's a rule for changing frames on momenta, just like there is for twists and wrenches. And it turns out, I'm not going to derive it, that the rule for changing frames of a twist or of a momentum vector is the same as the one for wrenches. So they sort of live in the same space. So the rule is H expressed in K of body I is a joint H K I transpose. So the transpose was for wrenches times H I. All right. So those are two things that we're going to need. Then let's see. So a very important property is that the rate of change of momentum, if it's expressed in world frame, so in an inertial frame, is equal to the wrench exerted on the body. So we have H dot expressed in world frame of body I equals the wrench exerted in world frame on body I. So this is basically Newton's third law. So that's really important. So let's take a look now at more than one body. So suppose we have a whole bunch of bodies. So these, and let's call this together our robot. So our robot's not going to include the world, but we just have a set of bodies that are that may be in contact with each other, and we call that our robot. So let's try to look at the wrenches that they exert on each other and that are exerted on them by the world. So let's write this. So this would be the net wrench on body I. And let's split that up into wrenches that are exerted by, on body I by other bodies. So the sum of J equals 1 through N. If we have N bodies of W expressed in world still, comma J I. And here the notation is the body that's exerting the wrench is here the superscript, and what it's being exerted on is the I here, is the bottom one. So those are all the internal wrenches, plus a wrench expressed in world frame exerted by the world onto body I. Okay, so that's kind of cool. Actually, doesn't show us so much yet. But if we sum up the rate of change of momentum for all of these bodies, for all of the N bodies in this thing we call the robot, we get this. Sum H dot W I equals 1 to N. So it's a double summation. Sum I equals 1 through N, sum J equals 1 through N. W J I plus W I. So it's and then this is still this only works for this. Okay, so now we have an even more complicated equation, but there's this really cool thing. Newton's second law says that a wrench exerted, that wrenches basically are equal and opposite. So really what Newton says is forces are equal and opposite, but that extends to wrenches. So if you have a wrench exerted on body I, expressed in world frame by body J, then there must be an equal and opposite wrench exerted the other way, negative Wij. And so if you work out this summation, this double summation, here, all of the terms drop out. Because for all of the internal wrenches, there's another wrench that's being exerted the other way, basically. So really, all that you've left is sum I equals 1 through n of w I. So only the wrenches, the external wrenches, applied by the world onto the robot, onto all of the bodies of the robot, matter in the rate of change of momentum of the robot as a whole. Because you could write this as h dot w. So this is the rate of change of momentum expressed in world frame of the whole robot, basically, which is just the sum of all of the momenta of all of its parts.
No, we shouldn't be surprised by that.
We should not, no. So that's really nice. That's a really cool property. So this is really nice. And then we also have this equation still. So we have the fact that each momentum of each body individually is a linear function of the twist of the body with respect to the world. And so the twist of each body with respect to the world can always be written as a linear function of the joint velocities. So for each of the bodies, we can write T I W I equals J I W I times V dot. Times V, where V is the joint velocity vector. So basically, we can construct a Jacobian for each of these bodies that takes in the joint velocity vector, the whole joint velocity vector of the mechanism, and computes the twist of just that body. And so before I made it so that this V was just the right size, like if we had joints here and here and here, and I wanted to know the twist of this guy with respect to the world, then I was going to construct a Jacobian from here to here that only considered as an input, so another joint here, maybe a floating joint, as an input the joint velocities of these two joints. But if you just add a bunch of zeros, then you can also work with the whole velocity vector. So we have twist of each body individually is a linear function of the velocity vector. Then the rate of change, the momentum of each body individually is a linear function of the twist. So along linear function of the velocity vector. Then if we differentiate this, then we get something like, well, if we sum all of these up, a sum of linear functions of velocity is still linear in velocity. So, well, yeah, the momentum of the body of the robot as a whole is also a linear function of velocity. And then if we differentiate it with respect to time, then it's going to be an affine function in velocity. So if we have sum of the h's in world is let's see, a v. So this, you can write this, right? So this is h w basically. So the integral of this rate of change of momentum. That's going to be a linear function of the velocity. So, and this is called the centroidal momentum matrix. If you express it actually in a centroidal frame. Otherwise, I guess you would call it the momentum matrix or something. But Ambarish Goswami also always expresses it in a centroidal frame.
The centroidal frame is?
It's like an inertial frame that's instantaneously located at your center of mass and has the same orientation as your world frame. Yeah. So you can write this And if you take the derivative of this, h dot w, that's a v dot plus a dot v. So this is linear in both the joint accelerations and the joint velocities. Now normally when you're controlling a robot, you can't instantaneously do anything about the joint velocities. So the only thing you have to play with is the joint accelerations, because you still have to determine that torques that determine the joint accelerations, basically. So this a dot v is usually known. So what's left is then, what we care about is that there's an affine equation in v dot. So it's not linear because there's this extra term, this plus a dot v, but it's still in a very nice form. Yeah, it's called affine. So now we have two equations for h dot w. So av dot plus a dot v equals the sum of all external wrenches. I equals 1 through n w I. And so this is going to be really useful, because now we have an equation that really concisely, because this is a 6D vector, so this is 6 by 1. We have 6 constraints that tell us exactly how which joint accelerations are allowed for a certain set of wrenches that we exert, external wrenches. And we don't, there's no torques in this equation, so that's nice. And really the only thing that matters is external wrenches, and not anything like you might be pushing against yourself. Again, there might be torques that cause internal wrenches between bodies. All of that doesn't matter. It all cancels out, and this is all you have left. Okay, so that's a really important thing.
So you can now look at your controllable space, so to speak.
Yeah. So let's do this. Let's try to write down another quadratic program. We're not quite there yet, but we're getting closer. So suppose we still try to achieve our motion constraints as well as possible. So we have this jv dot minus p squared, and we might also add the damp v squares term, v dot squared. So minimize this, subject to so a v dot plus a dot v equals sum I wi. And then here in this optimization problem, the variables to optimize would be v dot and then all of the wi's. I in 1 through n. If you allow wrenches to be exerted on all of the bodies. Now, for example, if you know that only your feet are in contact with the ground, then you basically get rid of a whole bunch of variables and only have 2 wrenches, and it still works. Yeah. Yep. All right. So that makes the size of the QP a lot smaller, because we get rid of taus. We still have external forces in the QP, but that's unavoidable. So we get rid of taus, and we get rid of like at some point we were considering maybe adding in the whole equations of motion as a constraint, mv dot plus c plus j transpose f equals tau. That's a whole lot of constraints, and here we have 6 constraints, no matter what the size of the problem is. So no matter how big your robot is, Sure, the v dot vector will grow, but the size of the number of constraints necessary in order to write down basically what accelerations are feasible for given wrenches, that's the size of that stays the same. So that's a really nice property.
You just lose the maximum joint torque constraints.
Yeah. So if you wanted to incorporate something like that in it, you could add m v dot plus c plus j transpose f, or I guess let's make it just w, all of the wrenches. Something like is less than tau max. So yeah, in order to incorporate maximum joint torques, you need to add a whole bunch of constraints again. But if you don't care about that, if you have sufficient actuator torque limits in general, then you don't need to do that. But yeah, moving forward, this stuff might be necessary. Yeah, because what hurts you usually when doing this kind of control is actually not being able to achieve these desired accelerations. Well, yeah, that's always a problem. Really, what we're trying to do is just come up with accelerations that satisfy the equations of motion. We're always trying to be feasible, at least. If you're trying to ask for something that you can't achieve, then who knows what will happen, right? We're trying to avoid that situation. So yeah, this can be a problem, but I don't think it wasn't a problem really for DRC, for the VRC, unless we try to do really weird behaviors like stepping up to something really high. It might be a problem now that we have the same actuators but a much heavier robot.
Also, tau max is not correct. It's probably a torque speed curve there.
Yeah. So you could have like a tau max dependent on v, but for every time step you'd have a v that's known.
Mm-hmm.
So yeah,
And
you
we
could
want to run.
incorporate that. Yeah. All right, but
And that's still convex, that constraint, right?
yeah.
The V's and the V dot and the W together.
Is the
all
C
in one.
convex?
Is what?
The C term.
C.
C.
So you can't really say that. So this is just basically a constant for this time step, right?
Yeah.
Oh, An equation like this is called affine, and an affine equation is convex. Yeah. Because
You can't have tau max be a function of V though. On the right.
well, yeah, you can. I mean,
For
so
time step you can-
v at a certain time step is known, is measured.
Oh yes, we're looking at V dot.
So yeah, we're trying to determine v dot. Okay, so the size of the QP is a lot smaller, and this is actually what I showed before with adding in the whole equations of motion. That's what Chris Atkinson is doing, and so at some point he was asking for a quadratic program solver, and we recommended CVXGen, like that's what we're using. And he was saying, oh no, my problem is too big. It says it can't generate code. And he found another quadratic program solver that actually could handle it, so we should probably switch to that. But that sort of shows the difference between those two approaches.
So it's
Other than that, it's
didn't
really
work.
similar. What's that?
You didn't get it to work in the end, right?
Yeah, you got it to work.
Fast enough?
I think so. He had all these really cool behaviors, but then he just introduced some stupid bugs. Okay, so size of QP is a lot smaller this way. However, we still have to incorporate limits on the external forces, or wrenches. So how do we do that?
I mean, because we have friction limits.
Yeah, friction limits, and also here we weren't saying, hey, you can't pull on the ground, right? Yeah.
One quick thing I want to interrupt you on, I should have, before you erased the previous slide where you had the wrenches, there you did have 3 letters for each wrench, whereas up yesterday or the day before,
Yeah,
we said
yeah,
you should have 3 letters on each wrench.
Yeah, so
It's just for the internal
yeah,
wrenches.
it's to make this
Oh, the
more
I and
obvious,
the
I and the J,
added
like,
letter was adding them up.
Yeah.
There's still only 2.
well,
It still wasn't, yeah.
It was just to show difference between
Look at the
internal
video.
and world wrenches.
all right. Okay, so now we need sort of a way to construct wrenches that are actually feasible. So what often happens is that you have some kind of plane, and then there's a point on the robot that's contacting this plane. So that's one option. So there's this surface normal and the friction cone like this. Right? That's one option. So this would be ground. And this happens, for example, if you're standing on your toe or something. Then the other option is that there's actually a plane. Let's see. Yeah. Yeah. The other option is that there's a plane, like a planar contact, so that there's a foot. That's just completely in contact with the ground. I don't know if it's really another option. So you have a whole bunch of contact points, for example, at the corners of the feet, and at each corner, there's a force that needs to be in the friction cone locally. So this is sort of the space that forces at these contact points can live in. Now, one way to treat these, to come up with constraints on those forces, is to actually construct them from basis vectors that lie in the friction cone. So instead of using actually a cone here, we're going to approximate that cone with a bunch of basis vectors that for this discussion are just going to have unit length. Let's see, is this making sense at all? So let's do it like this. So we have a pyramid, and then so this would be, for example, I'm going to reuse a notation, but beta I, and that's a unit vector that lies on the edge of the friction cone. So, and if we now construct a force by using only these unit vectors, these betas, so just as a linear combination of them, then we get F at contact. Let's call these beta ij. So this would be contact point j. So Fj is sum from I equals 1 through 4 to 4. So since we have 4 basis vectors in this case, beta ij rho ij, where this rho is some multiplier. So if we do that, then we get a force that's in this cone, right? Well, not quite yet, because we can also make these rows negative, and then we end up somewhere here.
Beta, ij, and what?
Sorry, what's that?
What is next to beta?
Right.
Rho.
Rho.
My row is in some row. Yes. So if you choose a row that's negative, then you end up with a force that's pointing in this direction. So you could have an Fj like this. And that's not what we want. That would mean that we're actually pulling on the ground with our foot. So in addition to constructing Fj from these basis vectors, we also need to say that all of the rows need to be positive. What's the sigma? rho ij larger than or equal to 0. So by just doing these two things, constructing them from these basis vectors that lie on the edge, and requiring that the multipliers are bigger than 0, you have forces that are guaranteed to be inside the friction cone. And like they're a little bit conservative, since like a force here that would lie in the actual rounded ice cream cone, friction cone, is outside of this pyramid, but a conservative estimate is better than the other way around, I guess. So if you add more vertices, then you add more, you increase the length of the row vector, but you get closer to the friction cone, actually. All right, so that's forces. Then the forces, the sum of all forces exerted on all of the bodies, basically, if you have a whole bunch of these contact points, is just a summation. So you get F equals sum over J of Fj. And since this Fj is a linear combination of the rows and F is a linear combination of the Fj's, you can write this as Qf times rho, where rho is a vector of all of these rows stacked on top of each other. And so we have we can write our additional constraint as rho larger than or equal to 0. So that's cool. Now we have the sum of all forces, all external forces exerted on the robot, as a linear combination of these rows plus this inequality constraint. Now we still need to do the torques. So we had this h dot equals sum of the wrenches, so W. And these wrenches have a force part and also a torque part. But if you just consider let me do this. So if you have a world frame here, and the location of this point in world frame is Rj, then the torque exerted by this Rj in world frame is just tau j equals Rj cross Fj. And we saw with that skew symmetric matrix thing, you can write that as Rj hat Fj, where this is a 3x3 matrix. So that's linear in Fj. So if we sum all of the torques exerted at all of the contact points up, then again we get something linear. So we have tau, which is the sum of all taus. Sum j, tau j is q tau times rho. And so putting this all together, we have W, or the sum of all W's, which is the thing that we had on the right hand side there, is Q times rho, where Q is Q tau, QF, and we still have the requirement that the rows are greater than or equal to 0. So now we're able to construct forces, or wrenches really, that satisfy the friction cone constraints. So that's nice. So how do we incorporate that into the quadratic program?
Yeah, those two equations.
Exactly.
Magic.
So we're going to minimize j v dot minus p squared plus lambda squared v dot squared subject to q times rho, so that's the sum of all wrenches, equals a v dot plus a dot v. So both sides of the equation represent rate of change of momentum, both linear and angular. And we add the inequality constraint, rho larger than or equal to 0.
And then, oh, you didn't have any other options.
No, not right now. And then maybe what you want to do is also try to minimize the forces that you're exerting on the world. So that's that might also sort of minimize torques, sort of indirectly. So you could add a term like this plus like epsilon times rho squared. And again, if you find certain parts of rho more important than others, you could make this rho transpose times E or big epsilon or something times rho, where instead of this E being diagonal epsilon, you could have something else, like another diagonal matrix, or if you want them to be dependent somehow, you could also put that in there.
So to end, before it was the contrary, like the constraint was on the joint acceleration, the motion the motion, and the momentum base, the rate of change of momentum was the objective.
Yeah.
So is it like right now you have changed that in the
no
control? Or
so this is again just another variant. You could actually add in a momentum rate of change objective as well. So plus a v dot minus b squared. So if you have a certain h dot that you want, an h dot desired, then that's going to be a v dot plus a dot v. So if you write that in this form, you get a v dot equals h dot d minus a dot v. So this would be b. And if you only want to achieve, for example, linear rate of change of momentum, rate of change of linear momentum constraint, you can do the same trick that we did for the joint, for the motion constraints, and just pre-multiply an s. So s a v dot equals s b, where, for example, for linear rate of change of momentum, you get s equals 0, 3 by 3 by 3. And the reason you'd want to have something like this is that the rate of change of linear momentum is really strongly related to instantaneous capture point motion, which is how we do our planning for walking. So we have instantaneous capture point trajectories, which I want to talk about today. Yeah, and also you can switch between having these constraints, or minimizing this thing, or having them as hard constraints. Yeah, that's sort of area of ongoing research, I guess. So you can either try to really achieve that motion, or die, or you can say just do your best. So, and again, you can weight it to determine what you find more important.
If you make it a constraint, then it can might violate the...
Yeah, it might not be feasible.
Oh, it will just crash, basically.
It'll say no solution.
It'll say no solution, but do its best to achieve the constraints if you have a decent solver, I guess, if you have a sort of a nice solver. But really,
But
there is no answer.
Then your momentum constraint can be violated.
Yeah. That's the first thing it throws overboard. Then, if you can't even achieve your constraints, why look at your objective function?
What time do you end?
3 minutes. All right. Okay, I'm just gonna read these real quick then for the video. So bad things about this is that like if there's unmodeled damping on joints with low attached inertia, for example an ankle joint, then that can cause bad tracking because really you're scaling by the mass of whatever inertia is attached to it. So that's a bad thing about this kind of stuff. In general, so you might want to like increase the gains for that or something. Model parameters are probably important for tracking, so you need a good model. Then, like some of the rules I use when constructing all of this stuff is like the number one most important thing I think is don't ask for things you can't achieve. Try to use feed forward at all times, because otherwise you just need an error in order to have effort. Don't over constrain us unnecessarily. So if you're trying to figure out what it is exactly that you want to do, and only try to do that and leave the rest free for achieving other constraints, I guess, or achieving other things. Try to decouple things as much as possible, so you do that with inverse dynamics. That's a big step at least. Yeah, and so if you've determined what you want to control, try to control it as directly as possible. Like I really don't like the way Fast Runner is going right now. Like it's somehow supposed to do everything at once, but you're never trying to. There's no one thing that tries to solve one problem at a time. Like later on, all of it with the mass matrix can be combined and whatever, but it's nice to have a level at which you can just separate problems and solve one of them at a time. And always be consistent in terms of what you use. So use the same state everywhere. That's kind of obvious. But also use the same model everywhere. You just have one set of model parameters and you use that everywhere. And an example also is if you have a class that calculates COM velocity, that should always be based on the actual joint velocities of the robot, because otherwise it doesn't match.
Don't filter half.
Yeah, don't filter half of the things. Always make sure that they're all, consistent. Like some ideas of stuff to do moving forward. A hierarchical quadratic program, where you first try to achieve like the main goal, which could be balancing. Then in the null space of that, you can achieve your motion constraints that you want. So moving around. I guess this would be at the highest level, because this is just your equations of motion written concisely. Another thing we can do is switch to Quadratic using eigen. That's probably faster, so that's what Chris Atkinson is using, and then we don't have like an upper limit or so much of an upper limit on problem size also. Quadratic++, it's a quadratic program solver, and somebody recently rewrote the software in C++ using eigen, which is a matrix library that's really fast. Better visualizers on satisfying constraints. So whether or not you can satisfy certain motion constraints that you pose. Yep. So that's it mostly. So how we did this up to this point was with this CVXGen thing, which is really cool. There's a website, cvxgen.com. You can basically write your problem down like this, where you have dimensions, just like my A matrix is going to be 3 by 3 or something, so you just define some scalars there. Then you define parameters. A is a matrix built up, well, it's a 3 by 3 matrix, so it's like n by n, where n is defined in dimensions. Then you define your variables, for example, v dot here, and the objective you're trying to minimize. So it's really nice. And then let me just show you what we're currently using. So it ends up looking like this, and then you can view it in this sort of formatted form, which is really nice. So here you have your row larger than or equal to row min. This is kind of old actually. But q row equals av dot plus c. You can rewrite it so that c appears. And then there's all kinds of properties you can have for all the matrices also. And then you can just click generate code, generate C code. Creates, basically creates your solver. And there is an upper limit to the size of the problem that it can generate code for. And it'll just give you an error if it can't generate code for it. So yeah, that's it.
So you said the Quadratic ++, that's the name, right?
Yeah, Quadratic ++.
Should be a bit faster.
I think so, yeah. However, I kind of want to do the hierarchical QP thing, and for that I think we might need to write our own QP solver, or ask the guys who wrote that paper for their solver or something.
Okay.
Basically, if you have a hierarchical QP, then you solve a quadratic program at the top level, and then if you step a level down, you have your new constraints, but also still the constraints for the old one. So the number of constraints keeps growing, and if you just use, if you just make the quadratic programs independent, then you're doing a whole bunch of extra iterations that aren't really required. So the solver they came up with basically keeps track of the constraints that are active, and those get transferred down the chain.
Okay.
So you can save a lot of time by that, but you need a specialized solver. And in that paper, if you have a whole bunch of hierarchies, like a whole bunch of levels, the problem ends up actually being slightly faster than if you just have a single hierarchy and use a solver for that. So that's really cool. Yeah.
Quick question. So during the VRC, we had two different ways of solving. One that we used for getting in the car, and one for walking.
Yeah.
Which one is this? And can you say it?
This is the second one. This is what we should be using.
This is what we used for getting in the car.
Yeah. And currently there's like a bug in the implementation. I put a to-do list on Confluence somewhere, and you can contact me.
Okay. And for the walking, so you could look for the walking, instead of having the JV dot minus P and the minimize, we had that in this subject too.
It was split up into two optimization problems, or optimization. I even forget.
Well, we kept projecting in the null spaces of.
Well,
no, sorry,
the thing was we didn't have our v dot in the optimization problem. We only had q row equals some rate of change of momentum that we want to achieve, and then we had a way of calculating our desired rate of change of momentum based on the joint motion constraints.
Okay.
But those motion constraints could be violated if the motion isn't feasible.
Okay.
So really, this is the right way to do it.
Right, so we should
Optimize both of them at
gotcha.
the same
So
time.
we should get this working for walking, figure out where the bugs are, and
Yeah.
probably make the visualizer, which might help us find those bugs.
Yeah, exactly. All right,
What's
around.
that with the